Hello, everyone. Hello, hello, hello. You're all logging in. Looks like we're up to 14 people. I'm sorry for the delay in getting up to speed to catch up with you guys. Anybody have any questions while we're waiting for people to log in? Rebecca, I'm hearing stuff, but it's breaking up. So I don't know if you just didn't have your speaker muted or if you're trying to talk to me.
Yeah, that was my bad. Just didn't have it muted.
Oh, that's okay. It doesn't bother me when background noise is going on. I mean, during class it'd be an issue, but you're all good. Anybody have any questions for us? We're in chapter 4. We should be finishing it up to this evening, / afternoon. I'm going to start putting them. I've started recording the recordings, the Zoom meetings. I'm going to record them to my local computer to see if that makes the digitized version better, and also that allows me to immediately upload them to YouTube. So that's what my plan is. I'm now going to take the videos. They're going to be saved to my computer, and then I'll put them on YouTube. And I'm because that's not straddled by or strangled, if you will, by the internet connection, the Wi-Fi, and all that good stuff. Maybe it'll get a higher resolution coming into the recording. So let me know what y'all think. If you've looked at any of the videos in the past, I just was told today that like all of them are crap. So that kind of makes me mad. But anyways, if you see they're looking a little better and you can make heads or tails out of the notes, that would be very, very helpful information for me. So I did set the homework dates properly. Test 2, which covers chapters 3 and 4, I'm thinking I'll probably make available Friday, and you'll have until probably Wednesday, because that's when I made the homework due as well. So I really want you to have ample time to do the homework. I would advise you to try to get the homework, both conceptual and problems, done by Sunday at 11:59, but I gave you the conceptual work due at 11:59 on Sunday, and the problems due at 11:59 on Wednesday. So that's why I'm inclined to give you both the weekend and Monday and Tuesday and Wednesday. So hopefully that'll help you guys. It's fine, baby. So anyway,
talking to my wife. 3 and 4, or just chapter 4?
What's that, Mario? I'm sorry.
Is that chapter 3 and 4, or is it just for chapter 4?
Just chapter 4. Oh, the test is on chapters 3 and 4, but yeah, the dates on the homeworks were already okay for the chapter 3. Of course, I got a policy that allows you to do it late if you haven't done it. But I think what I did was I made the 19th and the 22nd the due date for first the conceptual, and then the 22nd is the chapter 4. But double check that on mastering. Okay. Chapter 5 will be a week from then. Any other questions? Hopefully I answered Mario's okay.
Yes.
All right. So I got my dome polished, as y'all can tell. Ooh, look at it. So fancy there. Not a hair to be found, even less than I had the last time you saw me. Anyways, we're doing chapter 4. Last time I discussed with you the specifics of Newton's first, second, and third law. So Newton's really laws of motion, which I told you if I've seen further than others, only because I stood on the shoulders of giants, was a very modest type of expression, but had some, underlying meaning that was a little different. But the main thing is it was somewhat correct in that Newton's first law and Newton's third law had already been discovered by other people and stated in a different way. So just to rehash, Newton's first law of motion, one of two ways. Basically an object in motion tends to stay in that state of motion unless acted upon by a net external force. That means a net external force that is not equal to 0. So net means add up all the forces acting on the object of mass m, say. And external means don't take any forces that are part of mass m applied to other parts of mass m, because they're internal forces. So it's got to be something applied to something else. In other words, something other than the parts of mass m applying it to mass m. Another way of saying it, of course, more succinctly, is using the concept of velocity, which is a vector quantity and has magnitude and direction. So you would say an object maintains a constant velocity unless acted upon by a net external force. I told you how to write that into an if-then statement. And then, of course, when you can make something that's a valid if-then statement, the contrapositives will automatically, according to logic and reason, be equivalent. So that's true as well. but I also showed you how to do a converse and an inverse, which aren't necessarily true. Okay, just because the if then statement is true, the converse and inverse need not be true, but sometimes it is, and that's the case with Newton's first law. Newton's second law is that the net force, and again, we're talking about the net external force, the sum of all the forces acting on mass M by anything other than parts of mass M, all those forces add up to give you the mass M times the acceleration A, and of course the net force are both vectors. So what that tells you, since M can never be negative, is that MA and A are parallel. And since MA is equal to the summation of the forces, then the net external force and the acceleration has to be parallel. So that's a couple of different important facts. And then finally, the third one, which seems to be the least important, but as I told you, a lot of problems you just can't solve without it. And that is that for every action, there's equal but opposite reaction. But I wrote that as the force on object 1 as a result of 2, so that's F12 vector, is equal to the negative of the force on object 2 as a result of object 1. Again, that's a negative F21 vector. So notice by flipping the indices, I had to keep the same magnitude, but reverse the direction by putting a negative in there. And that's the same thing as for every action, there's equal but opposite reaction. And I argued after we worked out while we were working out the Tesla S-Plaid, basically the force, the average force that the Earth had to put on the Tesla vehicle to get it to accelerate from 0 to 60, which is of course 26.8 meters per second, 0 to 60 in 1.98 seconds. And we got this huge value. I think it was like 21,000 or something. Yeah, it was 2.94 times 10 to the 5th newtons, which turns out to be literally 3 metric tons. So like 6,600 pounds. Again, that's just average. And I was ignoring air resistance and frictional forces that didn't help it. So one of the key things you hopefully learned was that all that stuff, or me putting a force on the gas pedal, that's me part of mass M, putting a force on another part of mass M, so that's an internal force. So that doesn't count. The engine, which is part of mass M, applying a force to the transmission, which is also part of mass M, that doesn't count. The transmission putting a force on the drive shaft on the differential on the axle on the wheel, and the wheel on the tire. All of those are internal forces, and none of those are acting on the mass M externally. So ultimately, oddly enough, the thing that we call the force that impedes motion, i.e. friction, is in fact the very thing that makes the car go. So, don't fall for that bit that suggests friction is a force that stops motion. That's somewhat correct, but what you have to realize is in order for a car to go, it has to have some friction, because what's going to happen is it'll apply a torque to that tire and rim system. That tire and rim system will therefore rotate. And if that tire and rim system rotates with more force than the friction can supply between it and the ground, then it'll just spin out and not go anywhere. But if it happens to keep within the friction, available friction force that could actually happen on that tire, then the car will actually take off, and it's in fact the friction force on the rubber of the tire that's actually pushing the car forward. Okay, so that's a quick recap of what we did last time. This time I'm going to talk about how we apply Newton's second law. I'm not going to get into friction yet. I'm not going to get into rotational motion, but I'm going to give you some of the stuff that you have to deal with first. Like, for instance, whenever you try to apply Newton's second law, you really need a free body diagram. In engineering, they do a free body diagram, but they also do like a lot of times in statics, they'll do like or in dynamics, they'll do like an acceleration diagram and a free body diagram. We don't do that in physics. We do a free body diagram, which basically just, if you're not dealing with a large rigid body that could actually rotate or something like that, then the object will be treated as a point particle, and you'll just show all the forces acting on it. When we get into rotational motion and talk about torque and stuff like that, then we're going to have to treat the object as like an extended object, maybe like a bar or something like that. And you'll show forces acting on this side and maybe on this side at an angle and all that good stuff. Then you can't treat it as a point particle, but you can still treat it as a rigid body, which makes some simplifications, meaning that if you apply a force at this end and this end, the thing's not going to shrink or expand so that those forces are moving. So let's get started. The first thing I want to do is convince you that inanimate objects can supply forces. So I'm going to start off with an object. We've talked already about how weight and mass are related. So let me give you a demonstration of how that worked out and how I got that equation. So first off, what I'm going to do is imagine a ball just falling. And I'm assuming y'all don't want to look at the top of my head. So I'm going to put it on the document cam because I forgot to do that a second ago. Come on, man. This is some A material. My hero Norm Macdonald died yesterday, so I got to keep up his humor, which obviously I'm not nearly as good. But anyway, so you can imagine a little ball or something, maybe a piece of popcorn falling. If it's actually in free fall, we've already studied that. Free fall means it's falling with pretty much only the force of gravity pulling it downward. So there's no buoyant force, there's no air resistance, any of that kind of stuff. So a free body diagram would just treat that as a dot, and then in the negative direction, or if you chose downward to be the positive direction, which you're certainly able to do, then I would draw a red vector. Oh, actually, let's draw a blue vector, because a blue vector sort of looks like a positive ghost sort of scenario. So this object has a mass m, and it has a force due to gravity that we would call what? It's a W word. Oh my God, that looks horrible. That blue does not show up hardly at all in there. Maybe it does now. Anybody know a W word that refers to the force of gravity?
Weight?
Yes, weight, that's it. So that's the only force acting on a body in free fall. Does everybody understand that and make sense of that? Okay, so Newton's second law, which says the summation of the forces is equal to mass times acceleration. And I told you that breaks up into the summation forces in the x direction is equal to mass times acceleration in the x direction. And then there's another one for the summation forces in the y direction equals mass times acceleration in the y direction. And there's another one for z, so I'll put a dot, 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 okay? Now that we know that, I'm really just treating a one-dimensional motion problem, obviously an object going vertically, so I'll call that the y-axis, and I'll call down positive. One of the neat things you can do in engineering, as I've told you guys before, is you can just draw something like this, and you could say this is a positive direction, or you could say, let's say this is a positive direction, and maybe do this, and then everybody will understand if you draw that down is going to be the positive direction. So that's what I'm going to do now. So the summation of the forces, that's going to become just the weight, and that's going to equal the mass times the acceleration in the y direction. Okay, now we know the left-hand side, and that would say we could solve for A, but actually we know the right-hand side too. We know the object has a mass m. Can anybody tell me what the acceleration of something is if it's in free fall? Yes, which we call G, right? 9.80 meters per second. So now by just filling in those parts, we see the very cromulent, as I took from this Hitchhiker's Guide, or excuse me, the Skeptic's Guide to the Universe, as I took from that, the very cromulent equation, weight equals mass times gravitational acceleration. So when you put in a mass and acceleration in kilograms and multiply it by 9.8 meters per second, then you get its actual weight at sea level on the Earth. Okay. So that's something we're going to use repeatedly. I'll go ahead and put a little box around it and remind you that's an equation you're allowed to use. And later we'll even see how gravity causes this, as well as where that G comes from. Now, what I'm going to do is show you a case to introduce an inanimate object that applies a force. So let's say there's a 50 Newton crate. I've already talked to you about the size of a Newton. Newton is about as much as a quarter pounder weighs. And I may have screwed it up initially, but it's supposed to be about as much as a quarter pounder weighs after it's been thawed and then cooked and some of the juice is lost, okay? And probably even some of the meat, because 1 to 4 would be the right ratio if it was exactly a quarter pounder, but it's 1 to 4.448. or 1.1 to 4.45. Either one of those is fine. So this is a table, even got a fancy tapered leg, like Norm would produce in the New Yankee Workshop. And what I want you to consider is the free body diagram for this 50 Newton weight. So we know that weight for this object is equal to 50.0 newtons. Now, what we also know is that there is a force pointing downward, which is what we call the positive direction. And again, my blue marker doesn't write that well, so I'm making it really, really super bold. And that's actually the 50.0 newtons. If you wanted to know the mass, then you'd have to say, well, weight being 50 newtons implies that M is equal to 50.0 newtons divided by 9.80 meters per second every second, which gives you, I'll quickly do this calculation for you if I haven't already done it. It gives me 5.102 kilograms. And obviously I'm carrying one extra sig fig, so I'll underline that extra digit. So that really is the mass. We now have the mass, we have the weight, but we have a problem. Newton's second law would say the summation of forces equals mass times acceleration in the y direction. That's really going to be the only acceleration likely from this, because we see only forces in the y direction. But we said the crate is laying on the table. So what's the velocity of the crate right now? Anyone want to tell me what the velocity of the crate is?
Zero.
Zero. Yes, it's that easy. Okay. Now, if I come back in a couple seconds, what will be the velocity of the crate?
Still zero.
Exactly. And that's the key. Velocity being zero is not enough to make the conclusion I'm making. But a few seconds later, if the velocity is still zero, then it's a pretty good assumption that that means the acceleration is equal to zero. Okay, because remember, acceleration is change in velocity divided by change in time. So a snapshot of an object giving a zero velocity does not imply the acceleration is zero. In fact, there's cases, specifically when you're swinging on a swing set back and forth like this, weird thing happens when you get up to the highest point on this side. At that point, your velocity becomes zero, but lo and behold, your acceleration is the biggest it will ever be on that particular swing. Now, as you fall, you're speeding up, speeding up, speeding up, speeding up, speeding up. And then as you get to the bottom of the swing's motion, your velocity is actually a maximum, but at that point, your acceleration is zero. So you've got to de-link the velocity and acceleration and realize how different they are. So yes, a velocity can be zero when the acceleration is zero, or a velocity can be maximum when the acceleration is zero, or a velocity can be minimum when the acceleration is a maximum. All those weird things are possible. So with that in mind, we see that the acceleration of this is zero. So I'm going to go ahead and write that that's zero. Well, there's no way in heck you get one force equaling zero. So Newton's first law, which says an object will travel with a constant velocity, which in this case is a velocity equal to zero, if acted upon by no net external force. Okay, so we know the net external force must be zero because the velocity is a constant. Therefore, this whole force must be zero, and I only see one. Can anybody think of what's supplying the other force? Yes. I don't know who said it, but it's the person that's been answering a lot of questions. Jared, not from Subway, a different Jared. Just kidding. So anyways, the table pushes on the block. That's what I mean by inanimate objects do supply forces. If that bothers you a little bit, I get it. It totally it doesn't seem reasonable that inanimate objects apply forces. But this inanimate object was built specifically to hold things up like glasses of tea, remote controls, or often as left by me because, you know, my wife will leave me certain chores and it'll be a big pile of laundry on it. So that's why we make the tables that we do, so they can hold up a certain amount of weight. And in fact, you can see that they are doing that just by letting an elephant sit on it, and you realize, okay, the table's not quite ready for that kind of weight. So in fact, there is a force from the table. And in fact, that force is going to have to exactly cancel out this force to work out, as you'll see in a second. What we call that is the normal force, and I usually use F sub n. Sometimes authors will just use the letter N, but it's called the normal force. Okay, so the normal force, normal means it's sort of like perpendicular, but it's the mathematically correct phrase to talk about a vector or array being perpendicular to a surface. You call it normal. Whereas a ray or a vector being perpendicular to another ray or vector, you call perpendicular. Does that make sense? So that's what the normal force is. And from Newton's second law, we can say the summation of forces in the y direction is equal to 0. Again, that's because the acceleration is equal to 0. So now we get Fn, which is in the negative direction. So I'll put a negative in front of it, plus 50 newtons. Now, be advised, it makes perfect sense here because I wrote it first. If I'd written that after, I would have just wrote 50 newtons minus Fn. And that's because I don't want to waste the time writing plus minus, okay? This side says sum them all up. There's no instance in where you're supposed to be doing subtracting on this left side, okay? What's going on is you're adding things, but unlike actual vector magnitudes, vector components can be negative. So that's the two forces acting, a negative y component, which is pointing in the upward direction and therefore is negative Fn, and a positive y component, which is 50.0 newtons. So we list that as a plus a positive, and that's all equal to 0. So we immediately can determine that F normal is equal to 50.0 newtons, and it's upward, okay? And we know it's upward because specifically we drew upward that way and we put it in negative here, and this just gave us our magnitude. Notice the sign did not come out. If I'd put plus and plus there, then the sign would have come out negative and that would have made sense. Any questions on that? So that's like just another rudimentary Newton's second law type problem to make something sit right in your head, and specifically in this case to present you with a normal force. Show you that it exists, show you what it's called, show you how you solve for it. Now, I need to show you some other things about that and other stuff. So what I'm going to do now is I'm going to do example 2. Since no one seems to have questions about that, feel free to stop me if you do. I'm going to take that same crate now, which has a mass of 5.102 kilograms, okay? This time I'm going to use a more conventional coordinate system, and I want to remind you that this actually tells us 4 things. So that tells us the x direction, the positive x direction is to the right, the positive y direction is up, positive rotation is counterclockwise, and then finally it also tells you that z is coming out of the page. And the reason why it does is there exists a right-hand rule that you take your right hand and you lay your fingers like they form an axle that is the x-axis. And that allows you to put your hand any way you want to, as long as this part, which is like an axle, remains as the x-axis. All those directions are okay. But then you have to choose exactly the right direction so that your fingers can curl through the shortest angle to the y direction. So I'm keeping my thumb up, I'm keeping my fingers this way, I can curl them this way to reach to the y, and then my thumb will point in the positive z direction. Another way of doing it is this, sort of like you're holding maybe a pistol or something, in which case the finger that points to the target is the x-axis. The finger that goes in front of the trigger, which is perpendicular to the other 2 fingers, is the y-axis, and the thumb points perpendicular to both of those, and that's the z-axis. So that tells you a lot of different things. Now what I'm going to do is I'm going to say, okay, well, this is going to have a negative force acting on it, and that's going to be the friction force. Okay. And that friction force, for instance, let's call that, I don't know, let's say it's 5 newtons. And the symbol I use for friction, by the way, is F. Okay. So that friction force is pointing to the left. I don't know why I did it green, because I called that the negative direction. I really should have stuck with red. So now I'm going to change it to red because clearly I'm drunk. No, not really. I'm just playing. 5.00 newtons equals F. And now all is right with the world. Yay. Okay. Now, what we also have is a little ground that this thing's going to be sliding under. And I'm going to make some assumptions. Okay. In this case, I'm going to say basically the only friction force is this 5 newtons, and that's it. But there's another force acting on it, and that's you pushing this way on it at an angle of 30 degrees, and that's 30 degrees with respect to the horizontal. Notice I drew that one black because it's not parallel to the y-axis or the x-axis. I haven't, quote unquote, resolved it into x and y components yet. So I drew it just plain black. Does that make sense to everyone? This is me just trying to be pedantic and helpful. So I'm trying to draw this in a way that makes as much sense as possible. So my free body diagram, FBD, is going to be a dot whose mass is 5.102 kilograms. It has acting on it a negative force in the x direction of 5.00 newtons. It also has acting on it a normal force, as we just discovered. Of course, that one's in the positive direction. So I'm going to use this dreaded blue marker again. Blue or green sort of is okay for going for me. So that's that. And I'm going to call that F normal. And I'm going to draw it really, really boldly so y'all can see it, which I know is a problem. Okay. And then I'll also have acting on it the force of gravity, which is the weight, right? So that's pointing in the negative direction. So I'll draw that red as well. And that is 50.0 newtons. Now I've accounted for the friction force. I've accounted for the force of the ground up on the object, which we call the normal force. What I haven't accounted for is this guy. Okay. Well, this guy can be broken up into a positive component this way. And let's just call this force, I'm going to say it's 200 newtons, and I'm going to say it's given by the symbol F. So as a vector, it'd be F with a vector symbol over top of it. And I'm going to call this F sub X, which is clearly in the Y direction. And I'm going to call this right here F sub Y, which is clearly in the negative X direction. Does that make sense? So now I have to put them over here and say, okay, well, here's F sub Y. And I'm going to tell you that F sub Y obviously is 200 newtons times the sine of 30 degrees. And since it's downward, that's why I put it pointing downward here. So you probably remember exactly what the sine of 30 degrees is. Hopefully you remember your special triangles, and your special triangles, in fact, tells us that the sine of 30 degrees is 1/2. So this one's going to be 100.0 newtons pointing downward. Does that make sense to everyone? Now, in addition to that, we're going to have this X component, which is going to be the 200 newtons times the cosine of 30. Okay, I will put that right here. And I call this F sub x, which equals 200.0 newtons times cosine 30 degrees. Okay. This one was 200.0 newtons times the sine of 30 degrees. And this one is times the cosine. Of course, the cosine is √3/2. So this is just 200 times √3/2, which is 100 times the square root of 3. So that's 173.2. And that's actually the full number of sig figs, just like the 100 newtons is the full number of sig figs. So now, as I told you before, Newton's second law really in vector form just gives us two equations if we're dealing with 2 dimensions, or 3 equations if we're dealing with 3 dimensions. Right now, we're dealing with 2. I'm going to first attack the y direction. So I'm going to say the summation of forces in the y direction is equal to mass times acceleration in the y direction. But you're trying to slide this box across the floor, right? So we're not really considering problems where it's jumping up off the floor or diving into the floor or even bouncing up and down. So because of that, we know the acceleration in the y direction is equal to 0. Does that make sense to everyone why I'm saying the acceleration in the y direction is equal to 0? All right, so now all I have to do is fill in the left-hand side and set it equal to me filling in the right-hand side. I showed you yesterday how you can write just LHS and repeatedly work that out, and you can write RHS and repeatedly work that out with a string of equals. And then at the end, you can say LHS equals RHS. That's will keep you from writing a string of equalities when you know damn good and well that one step in there is not true. That happens a lot when you just sort of go stream of consciousness on something. So that's why I give it to you. So the summation of forces in the y direction, I see I got an Fn, which points upward. So that's a positive. I have a 100.0 newtons, which points in the negative direction. And I have a 50 newtons, which points in the negative direction. So that'd be negative 50.0 newtons. Remember, this is really Fn plus negative 100 plus negative 50. That takes care of that one, and that one. That's the only forces I see. That's why we use the free body diagrams to keep us from making boo-boos like that and missing out forces. So since that's all equal to 0, then I have that the normal force in this case is not, it's not the weight like it was in the case before. Remember, in the case before, we basically found the normal force was the weight. But now you're actually pushing somewhat downward in addition to rightward when we're trying to push this block. So you've actually forced the floor or table or whatever it's sitting on to supply a larger force. And in fact, that larger force will be, if I pull it over here, it'll be positive 100 plus positive 50. So that's 150.0 newtons. And all of that is to the proper number of sig figs. I gave 50 to 3 sig figs because the 9.8 was 3 sig figs. And that meant 1 decimal place. And then the 100.0 was 4 sig figs, but to the 10th place. So since we're adding, we're always going to go down to the 10th place. So that's our normal force. And that really is what we're asking. We're asking for A, the acceleration, and B, the normal force. That's the question we're trying to solve. I probably should have stated that beforehand. Sorry about that. But yeah, we're just examining a problem where you're sliding a box or a crate across the floor, and you're applying it with a force that's not perfectly parallel to the motion that you're trying to enforce. So you end up getting an extra addition to the normal force as a result of that downward force. In fact, if you pushed upward on it, you could see then you'd have it at this 100 newtons. If it was below horizontal at 30 degrees, then the y component of f would be vertical. So this quantity right here would be positive 100, in which case you'd see the normal force is actually quite a bit smaller, and it actually becomes negative there. So that makes no sense. But anyways, that's what it is. Okay. So we now have one of the answers. The normal force is going to be greater than the weight. And that's me trying to teach you something. The normal force is not necessarily the weight. We'll see later when we do inclined planes that the normal force is in fact quite a bit less than the weight. Okay, in those cases, here's a case where it's bigger than the weight. So all sorts of cool stuff. Now let's do the summation of forces in the x direction. And in this case, we actually want to know what the acceleration is. So we know it's going to be accelerating this way. So we're going to write the summation of forces equals mass times acceleration in the x direction, which really that's the only acceleration there. So I'm going to say the summation of forces in the x direction is just equal to mass times a. So the summation of forces, which is really my left-hand side, that's everything that's horizontal, which I think you can tell is this force right here, which is 200 newtons times the cosine of 30. Well, the cosine of 30 is √3/2. So when I multiply that by 200, the 2 cancels out, giving me the 100. And then I just got 100 times the square root of 3, which is at 173.2. That's in the positive direction. So I'll say 173.2. Now, the 200 newtons had 4 sig figs. So this is actually correct to 4 sig figs. Now, I also have this minus 5 newtons. So I'm adding a -5. But why waste all the time writing that extra stuff? And I'm going to say that's 5.00 newtons in the negative direction. And that's going to be equal to 5.102. Notice I underline that, kilograms times A. So now I've made a statement that is true. Notice it's separated by equals because it's true. This is the right-hand side. This is the left-hand side. When I subtract 5 from 173.2, I'm going to get 168.2 newtons is equal to 5.102 kilograms times A. So now I can say A is going to equal 168.2 newtons over 5.102 kilograms. That has only 3 sig figs. This one has 4. So the answer's got to be in 3 sig figs. So when I do that, 168.2 divided by 5.102. Uh-oh, chose the wrong one. That's going to give me 32.97 meters per second every second. Obviously, that's supposed to be the 3 sig figs. So that should really make this 33.0, to be honest with you. And that's what the acceleration is going to be. That's a big acceleration. So that's how you do it. Now, remember, we just finished studying kinematics. So that doesn't mean that's over. In fact, I could take a problem like this and then say, okay, assume this motion carries on for some time. Exactly how fast will it be going after 3 seconds if it started with an initial velocity of 2 meters per second? Okay, how far will it have traveled if it started with initial velocity of 3 meters per second after 3 seconds? All that kinematic stuff can now be applied with this A, okay? So just because we're out of kinematics and we're into dynamics, that doesn't mean you can forget thinking about kinematics anymore. You're still having to do that. So any questions on that? So those equations, x equals 1/2 at squared plus v0t plus x0, that's still in play. V equals v0 plus at, that's still in play. V squared is equal to v0 squared plus 2a parentheses x minus x0, still in play. If you have, and remember those are the x equals 1/2 at squared equation and the vf squared equals vo squared Those two equations are only true if the acceleration is a constant. The v equals v0 plus at is true if you're using the average acceleration, or it's always true if you're using a constant acceleration. And then there's that other equation that again is only true if the acceleration is a constant, and that is the initial velocity plus some final velocity divided by 2 is the average velocity. Now you can take the initial velocity at t equals 1 second, you can take it at t equals 84 seconds. The main thing is if you examine it over the interval that you're interested in, you do the initial plus the final divided by 2, that'll give you the average velocity. So those are all still fair game. All right, so let's try example 3 now. This again is just something I'm making up to try to teach you the key principles of the things you have to solve. So what we're going to do is examine a problem that you're all familiar with. I hope you are. I mean, I know I do a lot of things and show my kids a lot of cool stuff about this, and even well, actually I do scare them a lot more than they probably should be. My oldest daughter's now, you know, approaching 20, so she's a little less scared, but my youngest daughter, I still get to startle her a little bit. So one of the things I do is when I get on an elevator, you know, when it first takes off upward, you feel really heavy. So I sort of like exaggerate it and let my legs get weak, and you feel yourself go down, 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 or something like that. Well, I like doing that, and it's because partly because I understand the physics, and partly because it was interesting to me before I learned about physics. And the only other thing that I try to do is when the elevator is getting near its end, it'll start to slow down, and I feel really, really light. So I'll actually squat down and jump up real high. And I've even gotten so high as my head touches the top of the elevator. I really like that, and of course my daughters are mortified because I only have daughters, and you know, I do that whether there's people in the elevator or not, because I'm a bit of a moron, but I like it. You know, I have fun. So this is something everybody should do. Everyone should experience. So what I want to do is work out that problem and make sense of why you feel so heavy, for instance, when you first take off in an elevator going upward, and why you feel so light when the elevator starts to come to a stop when it's approaching your floor. So let's imagine an elevator. Going to be a box like this. And now inside that elevator, instead of me just standing on the floor, I'm going to put a, whoa, y'all don't want to look at my armpit and my shoulder? Y'all prefer to look at the notes probably? Yeah, I think that might be the case. So here you go. So here's my pretty elevator. And instead of me standing on the floor, I'm going to have me standing on a scale. Okay, so I'm standing on a scale. And really what that scale reads is your apparent weight, okay? I'm going to say this object is actually accelerating downward at 2.00 meters per second. So I'm just putting the magnitude right here. In fact, I'm going to do my typical like that, and that's my coordinate directions, okay? Now that I have that, I'm going to say my mass, M, is 100 kilograms, 100.0 kilograms, and I'm lying. I wish I weighed about 223 pounds. I'd weigh, well, I weigh more than 223. That's the important thing. Okay. So there's my mass. I'm going to draw a free body diagram. That free body diagram has my mass equal to 100.0 kilograms. It has the force due to the scale pointing upward. So I'm going to use green this time instead of blue, because blue really looks bad. So that's my F scale. And you probably understand that whatever force the scale has to apply, that's the reading the scale is going to give you. That's why I told you that that's the apparent weight, or my apparent weight. So that's the F of the scale. Now, in addition to that, I have my weight acting downward, and that's the negative direction. So that's 980 newtons, which is my weight. Okay. Now, again, if you're in a dynamics class, they'd have an acceleration diagram that you can go with it, but I'm really not paying any attention to that. I'm going to say the acceleration is negative 2.00 meters per second every second. Okay. So in this case, I'm just going to take the summation of forces in the y direction, and I'll say the summation of the forces in the y direction is equal to mass times acceleration in the y direction. That's the only acceleration there is. I'm going to stop calling it a sub y and just call it a. And you can see that I have this side, the summation of forces is going to have F scale being positive minus 980 newtons being negative. Again, this is a plus, but because the magnitude or because the direction's in the negative direction, the component is negative. So really, I should probably pedantically write plus negative 980, but I'm just reminding you instead of doing that. Now I put up the right-hand side of F equals ma. That's 100.0 kilograms times a. And that's the acceleration that I'm experiencing, which I don't know why I drew an arrow there because I actually know what that is, right? I'm trying to solve for the force that the scale's applying. So instead of putting a there, I'm going to actually write, okay, I'm just going to eat this little thing because clearly it doesn't want to behave. So I'm going to put, in fact, negative 2.00 meters per second every second for my acceleration. And that gives me the S scale is equal to 980 newtons. When I pull it over here, it's going to become positive. And then that's going to be minus 200.0, which is an extra sig fig, by the way, newtons. So you see, in fact, when the elevator is accelerating downward, my apparent weight is actually less by 200 newtons. That's 780 newtons. Okay, so hopefully that convinces you why you feel light when the elevator starts to accelerate downward in this case. Okay, you could also do it with remember the acceleration going downward is still a negative acceleration when you're slowing down going upward. So that's the same thing as if you were going at 3 meters per second and then you start to slow down as you're reaching a higher floor. It does give you a smaller weight, 780 newtons, okay, which is 200 newtons less. Now, if you had chosen A to be going upward, that's when you're taking off, then this quantity right here would have been positive, and this would come over here and be positive, and you'd see that you'd get 980 plus 200. So that's exactly why you feel heavier when you're taking off as well. So hopefully that teaches you a little bit about physics and elevators. Does anyone have any questions on that? Okay, there's two other types of problems I want you to solve, and a lot of this is about learning mathematical tricks that we use a lot in physics, some of which are kind of weird because your math teacher hardly ever uses them. So that's sort of the conundrum, is we want to show you some math tricks, and we're going to use examples to show you that. So one of them is this little fuzzy dice problem. So let's imagine some fuzzy dice hanging from a mirror of a car. Okay, this is going to be example 4. So example 4, we have a car mirror, which in perspective looks something like this. And then we have hanging from it some little dice that would normally be something like this. But in this case, it's actually something quite different. It's out here at some angle, let's just say theta. I'm going to work it out in terms of symbols, so we'll get exactly the right answer. Okay, in other words, we get the answer that works for all angles theta, not just this particular problem, which has, say, 30 degrees or something like that. So this fuzzy dice is sort of falling back that way. And what we know is the car is actually accelerating forward at A. Okay. What we want to know is, what is the angle theta? We're going to say the block or the dice has a mass m, and we're going to assume that the string, which being a string, can only be in tension. It can't be in compression. Strings, if you squish a string, it's just going to squish, right? So this is a string from which a fuzzy dice hangs. And ideally, we're treating the fuzzy dice as a particle, a point particle. So I draw my free body diagram, again, using the convention plus x, y, okay? I usually don't even require you to write x and y. I'm always going to assume your horizontal is x and your vertical is y. If it does something other than that, then you need to put the x and y on it. But if you do x is horizontal and y is vertical, then by all means use it without writing symbols. That's fine. So my free body diagram is basically a mass m. Okay. And now I'm going to draw my coordinate system, which I'm going to draw as pink. There's my x. There's my y. And the forces I have acting on it are one that's not been deconstructed down to its x and y components. So I'm going to draw that one black. And that's the tension T. Okay. And by the way, I'd like to know T as well. So T's question mark and theta's question mark. All I'm telling you is that the mass M hangs from a string. That causes a tension in the string. And when the car is accelerating at a certain acceleration A, which we're pretending we know, then this angle will be theta, and I want to know what that theta is. Okay. Now the other forces acting on the little fuzzy dice is in fact the weight of the fuzzy dice, which I'm going to write as mg right here. Okay. I will remind everybody though that there is an acceleration going on here, and A is assumed to be going that way. So I drew it in green just to make sure nobody could ever see what I had written. No, because that's the positive direction, and I thought it might be nice to write it in green. Okay, so here's where you're going to learn. What we have here is two unknowns. We have a T, the magnitude of the tension in the string, that we don't know, and we have an angle theta that we don't know. Okay. So we've got two unknowns. That means we need two equations. And I'm going to show you a way of solving a system of two equations, two unknowns that you probably haven't seen before in math. So that's why I'm showing it to you, or partly why I'm showing it to you. So I know that the tension will have a y component that's vertical. So I'm going to draw T sub y here. And that's, of course, going to be T times the cosine of theta. And the x component of tension, by the way, T sub x. I really got to get a better green marker because I really like green and red being used. That T sub x, notice it's opposite the theta, so that's going to be T times the sine of theta. Okay. So now I can take the summation of the forces in the y direction is equal to mass times acceleration in the y direction. And that's going to become, notice I've got a ty pointing upward and a mg pointing downward. So I'm going to say T cosine theta minus mg. And of course, this fuzzy dice, if we're going at a uniform acceleration, we're not going up and downhill, it's not going to accelerate vertically. So we're going to expect that a sub y to be 0 like we've done before. So all this is equal to 0, which I can write as a different equation. I'd call it equation 1, for instance, and I'm going to say T cosine theta is equal to mg, and I'm going to call that equation 1. Okay, you'll see why in a second. Now the summation of forces in the x direction equals mass times acceleration in the x direction. That is, in fact, the only acceleration. So I'm just going to call that A. Now, in this case, we've got forces acting, and it's pretty much only T sub x, right? So we've got T sine theta is the only force acting in the y in the x direction, and that in fact must be what's causing the acceleration A. So I'm going to write it m times A, and A is something we don't know. we'll call that equation 2. So we've got two unknowns. We don't know t, we don't know theta, we don't know t, we don't know theta, but we're pretending we know m and a. Okay. So our method to solving this is, let's divide equation 2 by equation 1. I think you can probably see by now why we're doing that. I will take t sine theta equals ma and divide that by t cosine theta equals mg. Now, in principle, you're really not dividing the equal sign, but you can put it that way if you wanted. So just to keep the mathematicians from beating me up, I'm going to write it like that and put a little space between them. And of course, the danger of this is if this side of the equation or this side of the equation, either one's 0, then division by 0 is undefined. You can get something that makes no sense. In other words, an aphysical solution. That's always a danger when you're using division. So we just got to make sure that's not the case. And in fact, it can't be the case, because the only way cosine theta is going to be equal to 0 is when theta is like 90 degrees. And you're not going to be doing that kind of acceleration. Okay. So when we divide this, look what happens. It's really beautiful. The m cancels out with the m, and the t cancels out with the t, which is impossible for you to see because my good green marker is a pain in my good green butt. Okay. So you see sine theta divided by cosine theta is just tangent theta and then a over g. So that's it. Theta is equal to the inverse tangent of a over g. So if you know a, you just got to divide it by g and then take the inverse tangent, and you got the angle theta. Now that we have the angle theta, we can plug theta back into either equation 1 or equation 2. And from that, we can figure out what t is. So I'm going to use equation 1, but I'm first going to interpret this in terms of a geometric figure. So my geometric figure is going to be a triangle whose angle is theta. And then tangent equals opposite of our hypotenuse, so through our alley. So, excuse me, opposite over adjacent. So the A would be here, and the adjacent, of course, would be G would be here. And this is equal to A squared plus G squared, square root. Does that make sense to everyone? The reason why I'm doing that is I'm just interpreting this, but notice now I can take equation 1 and I'll call this equation 3 and equation 3, and I will get that t times the cosine of theta is equal to mg, which means t, now the cosine of theta is adjacent over hypotenuse, so that's going to be g over the square root of a squared plus g squared. So that's t times the cosine of theta is equal to mg. So you can see t is going to, in fact, be equal to mg divided by all this junk. So that's mg divided by g over the square root of a squared plus g squared. And of course, you all know when you divide a numerator by a fraction, you just flip over the fraction. We can already see that these g's are going to cancel one another out, and we're ultimately just going to get t is equal to m times the square root of a squared plus g squared. And that's it. Notice that is a unit of force because a squared or g squared both have the units of meters squared per second to the 4th. So when you take the square root of that, that becomes meters per second squared times kilograms, which is in fact a Newton. So we can call that equation 4. But there's our answers. But this technique, dividing one equation by another, is something that I never learned from the mathematics instructors, but I did learn it in my physics class. So I wanted to make sure you guys are aware of that. Any questions on that one? Okay, so now I want to try another problem. And this problem is, let's say there's a little kid hanging from a clothesline playing a game. Okay, so this is example 5. What we have is a clothesline that the left half makes an angle of 60 degrees with the horizontal, and I can call that 60.0 if I really want, okay? And the right half makes an angle of 36.9 degrees. And here's the little girl. Okay, hanging from the line. Okay, what I would like to know is what is the tension in the rope. So basically what we're going to have is a tension T going this way, which I'll call T to the right, and then a tension here going this way, which I'll call T to the left. And I'm going to say her mass is M equals 50.0 kilograms. Okay, now the girl's hanging, so she's assumedly not her velocity is 0, so she's has no acceleration because velocity is not only 0 but remains 0. So this is really a statics problem, which those of you who've taken statics probably understand already. But what we're going to do is draw a free body diagram and draw the forces on it. So we have a mass M. We have acting on it, of course, a tension TR. I'm going to use my typical coordinate system setup where right, positive, and counterclockwise and up are all positive. So there's my X, there's my Y. And I'm going to have, of course, this is 36.9 degrees, which hopefully y'all remember from your 3, 4, 5 triangle. And this also isn't going to be aligned on the axis, so I'm going to draw it black as well. Only this angle is going to be 60 degrees. Okay. And then finally, acting in the downward direction, which is negative, we're going to have a weight mg like that, which you can tell is basically 490. Let me see, 9.8, that'd be 98 times 50, that'd be, yeah, 980, then divided by 2. Yeah, okay. So yeah, you can get that. So everybody sees that right now, right? Now what we have to do is we have to break this up into components. This one, of course, is actually going to be positive, so I really should draw that green. And this one's also going to be positive, so I'll draw that green. So this is TR sub Y, and this is TR sub X. Got to get some better markers. Good Lord, that looks horrible. Okay. This one, on the other hand, is definitely in the negative direction. That's going to be TL sub X. And then this one's in the positive direction. And that's going to be TL sub Y. So it does look like we have 1, 2, 3, 4 unknowns, but in reality, all we have is TR and TL is unknown because we can relate TRX and TRY with the angle 36.9 and TLY and TYLX with 60 degrees. So we really have 2 unknowns. We need 2 equations. What we know is the girl is sitting still. She's not accelerating. So the summation forces in the x direction equals mass times acceleration in the x direction, but the acceleration in the x direction is 0. And then we have the summation of forces in the y direction equals mass times acceleration in the y direction. But again, that acceleration is 0. So we can ultimately write, notice in the x direction, I got TLX is going to be negative. So I'll put a negative there. And in fact, it's opposite the 60-degree angle. Notice it's down here. So I'd have to either use 30 degrees and it'd be adjacent. But since I'm using this angle, that's 60 degrees and it'd be opposite. So in fact, I need the sine of 60 degrees. And of course, you know from your 30, 60, 90 triangle that the sine of 60 degrees is √3/2. So what I'm going to say is that TLX is going to be TL times the square root 3/2, because that's what the sine of 60 degrees is. Now in the other x direction, I have TR sub x. That's a positive direction, so I'll just put a plus here. And I'll have a TR. Now this time, again, I'm going to have to go the opposite of 36.9 degrees because it's down here, and otherwise I have to use 53.1. That would be acceptable. I could use the cosine of 53.1, but instead I'm going to use the sine of 36.9. And of course, the sine of 36.9 is 3/5. Okay. All that has to add to give me 0. I'm going to give a little indicator what this is in case you guys got lost on my trickery. That's the sine of 36.9 degrees. And this is the sine of 60 degrees. Okay. Now over here, I'm going to have something similar, only now I'm going to have to use the cosines because I get the vertical components and both of them are positive here. So the cosine of 60, I think you can all guess, is 1/2. So this is going to be TL times 1/2 plus TR times the cosine of 36.9. And of course, the cosine of 36.9 is 4/5. And then I have a minus mg. So it's going to be minus m times g, and all that's equal to 0. So there's no ambiguity what this is supposed to be written as. I'm going to erase that and draw it again with a minus. So this I'm going to call equation 1. This I'm going to call equation 2. And what I can do is I can take equation 1 and say, let's say we're going to solve for TL. Okay. So TL, if I pull it over there, then it'll become positive, and I'll have 3/5 TR is equal to √3/2 TL. So I'm going to say 2/√3 times 3/5 times TR is what TL is. So there's a way you could actually reduce that. Square root of 3 divided by the square root of 3 is just a square root of 3. So I can actually call that the 2 times the square root of 3/5 times TR. And we'll call this equation 1 prime. So TL is that. Now I'll put 1 prime into 2. When I do that, I get TL, I get 1/2 of TL. Well, TL is actually equal to 2 square root 3/5 times TR plus 4/5 TR. And then all that equals mg, because I just went ahead and pulled the mg to that side. Does that make sense to everyone? So now doing that, I can see that 1/2 is going to cancel out with that 2. So I get √3/5 plus 4. So I'm going to say 4 plus the square root of 3/5 TR is equal to mg. or I can say TR is equal to 5 mg over 4 plus the square root of 3. And I could plug in the 50 kilograms now if I wanted to, but I really don't need to. That's a generic enough answer where now I can solve it for any mass m. Okay. And now that I have TL in terms of TR, all I have to do is multiply this nasty beast by 2 roots of 3 over 5. You can see the 5 is going to cancel out. And then I get 2 roots of 3 on top over the other thing. So finally I get TL is equal to, again, the 5 is going to cancel out the 5. So I'm going to get 2 root 3 over 4 plus root 3 times mg. And that is my actual two tensions, the left and the right side. Okay. Now, the last thing I want to show you, I think that's straightforward enough, but I quickly need to show you an Atwood machine, and that's not as hard as you might think. So let's imagine this is going to be example 6. Imagine a pulley that's actually massless and frictionless. And then let's imagine there's a big mass here called big M. And way down here is a little mass called little m. Okay. The key thing with this is I've got to decide a positive direction for some axes and then stick with it, or else it gets kind of complicated and things cancel out. They're not supposed to. So what I'm going to do is do a free body diagram for the left-hand side. So left-hand side, FBD. Okay, and I'm going to call up, well, actually, I'm going to call down positive because I suspect since that's a big M, that's supposed to be bigger than the little m. So I suspect it's going to go downward. So in fact, what I'm going to do is draw a mass big M. And I'm going to say acting on it is a tension T, because according to this box M, a little m, a big M, it is trying to fall down at 9.8 meters per second, but something's slowing it down. So it's going to see this as a T acting in the negative direction. And let's call purple the bright color that we're going to use for the positive X direction. So I won't have to use that stupid green or blue anymore. And acting this way in the positive direction is going to be big MG. And in fact, I'm going to call that my positive Y direction. Now, what that means is anything consistent with this big M going down like this, that's going to be a positive direction. If you go over here and think, well, when this goes up, that's the same thing as the big mass going down, then what you see is the right-hand side has to have up being positive. So I'm going to do right-hand side free body diagram. Notice there's 2 bodies here, so it's really good to write a free body diagram for each, and then you write a Newton's second law for them. So in this case, I have a mass little m right here. It has a tension, and by the way, it's the exact same tension as before, because in order for those to be different, it would have to have this thing having some friction or some kind of weight, because basically this thing says, hey, I'm being slowed down, and the amount it's being slowed down as a result of this guy, not any friction or inertia or mass of this thing. Well, this one's being brought up by the weight of this thing, and if this one had any mass or inertia, that force would be decreased a little bit. So these two have to be the same tension. So I'm going to say on this side, I've got a tension T pulling it up. Notice I drew that purple because that's the direction of the left-hand side going downward. And then I have a negative force acting downward, and that's negative mg, or that's lowercase mg. Okay. So Newton's second law here, the summation of forces equals mass times acceleration. What I'm trying to find is the tension in the cord and the acceleration, which, if the string's not going to become slack or stretch, then the acceleration should be the same, because if this goes down 1 centimeter in 1 second, then this is going to have to go exactly up by 1 centimeter in 1 second. So the 2 accelerations have to equal the same, just like the 2 tensions have to. So this side, I end up getting, let's say I'll work it in black. I'm going to get, for this side, I'm going to get big MG minus T is equal to big M A. Call that equation 1. On this side, I have the summation of forces equals mass times acceleration. Again, the accelerations are the same, but this time the T is positive. So I'm going to say T minus mg is equal to little m a. That's the key. Remember, we're doing a free body diagram for this object and for this object. So that's why I use those mass. That's going to be equation 2. And the big trick here is to actually subtract them and actually add them, I should say, because notice the T and the minus T have opposite signs. So I'm going to say 1 plus 2. You get T plus negative T gives you 0. And then I get mg minus mg is equal to m plus m times a. So you can immediately see that a is equal to m minus m over m plus m, all that times g. And that is, in fact, the acceleration of the Atwood machine. But that trick is another mathematical trick. One, you got to know you're dealing with two bodies, so you should draw two free body diagrams. Unless you don't care about the force between them, then you could pretend they're one and the same, one big mass. But that's a little more complicated, and it gets kind of convoluted to work it out. Now, if you want the tension, now all I have to do is plug that in for A, and ultimately what it's going to become, if I remember correctly, is T is going to be equal to 2m1 m2 over m plus m. I don't know where I said m1 and m2. That's another way I do it. And this one's just going to be plain little m. Y'all can verify this algebraically on your own, but it's going to be 2 times little m times big M times g, and that will be your acceleration. Okay, we're done. Class is over. It's actually 7:03, so you guys are free to go 3 minutes ago, actually. But we've now finished chapter 4. The test is going to come open Friday, and you'll have until Wednesday to get that done. That's on chapters 3 and 4. So make sure you get that done. But like I said, if you forget it by Monday, you'll get a chance for your students to remind you. The big thing is I would probably try to do it as soon as you can, just to make sure you have one score under there in case you forgot it. Okay. So everybody's free to go. If you have any questions, stick around and ask me. Otherwise, I will see you next week. Thank you for coming, everybody.
Thank you. Have a good weekend.
Thank you too.
Professor,
Yes.
I know I should have told you this before, but I was waiting for financial aid to get my textbooks, and I literally just got my access code today.
Go.
And I'm trying to get, I know. Well, I did some of the homework, because I had the 2 weeks, but it ran out, and yeah,
Gotcha.
it just.
No problem.
Yeah, I'm
Once
just
you put the
trying
code
to.
in and you get those 2 done, just let me know. I'll give you credit for it.
Okay, thank you so
Okay.
much.
No problem. Just remind me, tell me exactly which ones you did after the due date, and I will correct those scores. Okay.
Okay, thank you, Professor.
You're welcome. See ya. Anyone else have any questions?
I had 2 questions
Yes.
about the lab I'm in.
Okay.
So one question is that we have an unpublished lab assignment due tonight for lab 4.
Is that my class or someone else's?
Yeah.
Okay.
And
Nothing should be due tonight. That must be something that was left from where I copied over a course. The only thing you have due, if your lab met today, then your lab was due today at 1 p.m. If your lab meets tomorrow, let's say at 8:30 in the morning, which is one of the classes I have, then the lab that you did last week on Thursday at 8:30 in the morning is now due tomorrow morning at 8:30. So your lab's always only going to be due on at the beginning of lab time, the next class period, the next lab period, I should say.
okay, I just wanted to let you know.
Yeah, thank you for that. And I'll try to find out what that assignment is, and just don't worry about it. Like I said, you didn't have to do anything there.
Okay.
Thanks, Jared.
And
go ahead.
I had one question. I had my lab 3 attendance. I got a 50 on it.
Your
Even
name's
though
Jared Cochran.
Yeah, I showed up to the lab and I actually asked you a few questions as well during the lab.
This was last week's lab, and you're in which class? The Thursday or the Friday class?
The Friday class.
Friday class. I made some corrections today, and I made somebody's correction that their first name started with a J. It might have been you. Have you looked at it since, say, 1 o'clock this afternoon?
Yeah, I'm looking at it right now.
Okay, it still says 0 or it says 50 out of 100?
It says 50 out of 100.
Okay, and that's for last week's lab, not the week before.
Yes.
Okay, I
Last week's.
will correct that. If you don't see it corrected by lab time next time, just let me know and I'll fix it then. But I'll do my best. I probably will remember. Okay, I ended up having to trade like column 1 with column 2 at one point because I realized I did the wrong day. So it could be as a result of that. And I've been trying to go back through and correct all those, but leaning heavily on my students catching it. So if you were
Okay.
there and you were there in excess of 30 minutes or so, then chances are you should have gotten the full 50 points for being there on time.
Okay, cool.
Okay.
Okay.
All right,
Thank
see
you.
Jared.
That's all. See you.
Thank you. Hassan, do you have any questions? All right, well, I'm going to call it a day then. Have a good one, everybody.